Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're gonna take a look at geothermal energy that is infinite. Now in my last day's episode we talked about geothermal that we have, but I'm here to talk about the future. So let's dive right into it. So first you have to understand what are our current limitation, as in like we already have geopower, but why we don't have infinite geopower. There are three core components of it. First, component number one, depth. How deep can we go? Now this is the deepest bore ever done by humans. This is in Russia and it only goes to 12.26 kilometers. That's not deep enough. Like, of course, as many of you know, we don't need to go to the core of the earth, but we need roughly 20 to 30 kilometers. Like at 20-30 kilometers you can power a civilization, but like 12 kilometers is good enough, but it took freaking decades to drill this far. Then okay, let's say you somehow managed to do that, let's say somehow you managed to get that, then second problem becomes how you're going to transport that. And then once you transported the energy, however amount of loss you suffered, how you gonna convert that heat into electricity? So these are the three current problems. So let's look at them one by one. So first, drilling. We cannot use hydraulic fracking. Basically, we tried this. Problem is it causes earthquakes. So not a desired side effect. And not to mention, this also increases the chance of emissions happening because of them, because natural gas is trapped in many of these places. That's why we use hydraulic fracking in the first place. They can start to leak out. So you will end up with emissions in the first place. So then once we get that, we can't use that. Then how are you going to drill it? Now, many of you know drill bits. This is the drill that did the deepest hole on earth. Now what they did with this was quite ingenious. Generally many of you have seen drills that rotate the whole shaft. What they did is this: instead of rotating the whole shaft, they had a pressurized drill mud that was pumped down, and here there was a hydraulic motor that was rotating using that pressure. Rather than rotating the whole shaft, it was just rotating the whole thing. So we have to do something like that. We could in principle make an electric induction motor roughly of like 500 or 600 horsepower, and that way, like, the reason why I'm saying 500-600 horsepower, it's not that we need that much horsepower, is that at that high temperature, upwards of 500 degrees Celsius, we can't use BLDC because the magnets will lose their power. Induction motor has to work at very high voltage, so we don't dump too much amp onto it. And benefit of high voltage is that it reduces the amperage and also improves the torque of the motor. So we could have like 3-phase or 6-phase. If 6-phase might actually allow us more benefit, since it will improve the torque performance by 12%. So 3-phase or 6-phase, whatever method, but we have to come up with a point where we can only rotate the drill end, not the whole shaft as you see in the oil drill systems or any normal drill where you're rotating the whole thing. That's not gonna work flat out. Then the new kid in the town is laser drilling. Now this is a 20 kilowatt laser drilling demonstration that was done, and what they are doing is very crucial. They're not vaporizing the rock. This is very crucial. I originally thought that we can just fire very big laser. The problem is that even if you build a big laser, lasers are very inefficient, as in they barely convert 20% of energy. So is consuming 100 kilowatt, only giving out 20 kilowatt. So okay, let's say somehow you connected it to a grid and you're like, okay, I'm gonna run it at full power. Problem is that is gasification. Basically, if you hit a surface, whatever it is, rock, metal, whatever, if you hit it with laser that is way too powerful, as in powerful enough to damage it, it will turn it into gas. Now problem with that is that gas will start to come out. Of course it will try to go sideways also, because there is a lot of photon pressures, but it will block the laser from going forward. So how they are bypassing it is very crucial. Their core goal is to reduce the energy consumption on drilling by 90%. So what they are doing is, generally instead of rotating the shaft, they are doing the same thing, only rotating that. And generally it used to take 1500 horsepower, as in roughly 1 megawatt, more or less 1 megawatt. They can do that at few hundred kilowatts on the rotation end. And with the laser, what they are doing is they are fracturing the rock. Basically they are giving enough heat that rock becomes kind of brittle rather than vaporizing it. This way, they both combined, they can save a lot of energy, and this way they don't have to worry about gases coming out, that is, you know, pressurizing everything. Because if you have a very powerful laser, you can drill very deep, but problem is the gases that will be coming out of that itself will slow down your progress. So, and we don't have lasers that are that powerful. So for flat out, this is the best approach as of now. and I have linked the data in description below. So this is how we have to solve the drilling aspect. Now we have to worry about transport. Now this is a very common, as in like you can think of it as a rough diagram of how most geothermal works. Now this is the danger aspect of geothermal. This is why earthquakes happen. This is why emission happens. It's not solid state. As in what they do, it's called there is a well there where they'll pump water in. Now the well is of course sealed, but as it goes down, it does not come in a complete loop. It goes and it's exposed to the rocks. This is what causes hydraulic fracking and earthquakes and destabilization of mineral, because water is evaporating in a place where it's very hot. Obviously we want that, but problem is it's evaporating and seeping everywhere. So not only there is an inherent loss of water, like let's say you put 100 tons of water, you're not going to get 100 tons back out of these things. Extraction wells basically they are called. So for that reason, not only you are losing a lot of water, you are also causing emissions, because those are being absorbed and pushing CO2 out there, pushing whatever is already there, pushing those things out. So for that reason we cannot use that. And not to mention, this is idiotically wasteful of water. Now it's nowhere near as much wasteful as coal power plant, but it still does waste a lot of energy. For that reason we cannot use that. We have to go solid state, either by a copper wire or what everybody is linked in the description below, graphene. The reason for that is graphene is very conductive. Now of course in that video that I'm linking to, they are saying the graphene will, like if you have a rod and you heat 100 degrees Celsius here, it will goes to that side 100 degrees Celsius. Absolutely true. They say the center remains cold. Yeah, that's not happening unless you insulate it. However, even with that, because these rocks acts as an insulator, you're not gonna lose too much energy. So it is compulsory that we figure out how to make graphene and how to do solid state. Without solid state, the risks are very serious. So once we've done the drilling, once we've done the transporting, how we convert that energy into electricity. Now we cannot use steam cycle, because not only that the well that we are doing is also wasting water, the steam cycle is inherently wasteful. As many of you have seen that cooling towers that we have, you see steam coming out of that. Inherently there should not come out of that, because it's wasting water. So let's say you found a geo spot in a desert, you can't use that because you have to transport insane amount of water there to run a steam cycle, and steam cycle are generally very efficient if you have very high temperatures. So you're not going to get very high temperature from geothermal. At best case scenario, you're going to get 2 to 500 degrees Celsius, not 2000 degrees Celsius as you can get in coal fire power plants. So for that reason steam cycle is out. My primary reason for that is basically you don't want to waste water. Second, what we're gonna use instead is called Stirling engines. Stirling engines are very efficient, they are very quiet, and they are internally sealed, as in there is no working fluid going in and working fluid coming out. So the efficiency of Stirling engine is almost at par, at some scenarios exceeds steam cycle. The reason why we don't use Stirling, if water is first, all the coal fire power plants are ancient and we know how to use that, so we just stuck with it. And in this sort of scenario we have to use Stirling. This will allow it to be used anywhere, like let's say sub-Saharan Africa where you don't have enough water, you can't run steam cycles there, you can run Stirling on there. And let's say Stirling cycles have been used in solar industry for quite a while and they do quite a phenomenal job. And we also have to do what's called geo heat seeking. Basically, because Earth's core is there, and if you're transporting that, the core itself, the crust itself is acting as a basically insulator. You have to dump heat in that insulator. Reason for that is Stirling engine works best if the temperature gradient is high, as in like one side is let's say 500 degrees Celsius, the cold side is 60 degrees Celsius. Now if you are in Africa, the air temperature reaches that hot. I live in India and I have walked outside where the air temperature was peaking at 60 degrees Celsius. 50 degrees Celsius is quite common for us. So in those sort of scenario, if you have an air cooler, it's not going to work very effectively. However, geothermal cooling in those sort of scenario, because Earth barely gets to 30 degrees Celsius, is going to allow extra benefit. However, if you are in a place let's say like Ireland or Iceland, basically if you have cool air, then you're going to use air cooling. So that way we can extract the heat much more effectively. If we can create enough temperature gradient, we're going to convert it much more efficiently and we're going to get our power. So these are the three core problems that we solved. Now let's look at some hurdles that we're going to face. Now first thing is time to drill. anything is directly proportional to the time. Basically the profit, money talks. So if you say to someone that I'm going to build a power plant, a solar power plant takes 1 year to 2 years to build, a coal power plant can take 5 to 10 years, dam could take a really long time. Now this, if you come to say and like we're gonna drill and it's gonna take 30 years, they're gonna be like, yeah, no thank you. So we have to cut down drill time from years to months. It's compulsory. However, I have faith in that laser drilling technology, because they have already proven that it works, and many Israeli oil companies, including Iraqi ones, they are investing a lot of money into that, and including Department of Defense from USA is also investing a lot of money into that. So technology is proven. We got the technology working, we just have to refine it. Basically, we got the first mobile phone, now we have to make higher versions of smartphone. Then we also have to do what's called horizontal drilling. This is not needed if you have open cycle. Basically, if you're dropping water directly, you don't need that, but we don't want to do that. So we have to do what's called horizontal drilling. Thanks to oil exploration, we know how to do that. You can have a oil, basically drill bit go directly down upwards of 10 kilometer and then directly take a 90-degree turn. However, it's not 90-degree like that. It's like a curve. It's a smooth curve that does that. The reason for doing that is you have to maximize the area. If you have, like, let's say you directly drill it, you're gonna get few kilowatts of power. But if you drill there and then you, like, let's say create loops or lot of loops of basically pipe or carbon nanotube, if we ever figure it out, or graphene cables, that way you can extract lot more heat out of it without needing to resort to open cycle systems. So for that reason, we have to maximize our energy output. We already did the hard part. Drilling horizontally is not that difficult. We have already figured it out. So once you go down, you have to go horizontal to maximize the energy output, and you can have it running continuously, as in, like, let's say your power plant started working, you can still expand it. That way you can make sure as the city grows, you can keep expanding the system to provide more energy. So we have to do that. Then we have to build something known as the Stirling Engine. But Stirling Engine right now is it's not that big of a word. Like, the biggest Stirling Engine single stage I can find is used in a submarine because it's stealth. It does not produce too much noise. So for that reason, the Stirling cycles that we have today, it's built for high temperature difference. We have to build something that is more efficient at low temperature difference, because you have to make sure that you are you can take 100 degrees Celsius and get 50 degrees Celsius work out of it. So for that reason, there is a temperature gradient. The bigger the gradient, the efficient it becomes. We have to make it such a way that we can, because the outside temperature can be as hot as 50 degrees Celsius, we have to design the system that if we are only getting 100 watts, 100 Celsius, we can make our engines work at that 50-degree gradient. Will Stirling engine work? Yes, it can work at the temperature of your body. You put Stirling engine in your hand, it starts to work. So it can work, it's just we have to refine the design so we get more efficiency out of it. Then we have to talk about graphene. Basically, it's the most untested part of it. Not to mention, nothing can actually transport 100% of energy to 100% of the distance without any loss. Physics does not allow you to do that. How much loss is there? That will directly depend on the quality of the graphene. Like, if it's a very good quality, you are talking about 10% loss. If it's a bad quality, you are talking about 80 to 90% loss. For that reason, we have to make sure we have very good quality control on those cable. And you are talking about 20 to 50 kilometers of cable. For that reason, we have to be very careful about graphene. Then we have to worry about emission management. That deep hole where it started to find hydrogen, as in raw hydrogen started to come out, and as many of you know, rocks have lots of oxygen into that. Because of those high pressure and presence of hydrogen that is trapped there, not going down there, trapped, as in at the creation of Earth it was trapped there. They both mix and voila, you get water out of it, as in high pressure water out of it. So we have to figure out some way to manage it. And there will be some emissions, even though you use solid state. At the time of drilling, there is a lot of gases that's going to come out. So we have to figure out how to handle arsenic, mercury, methane, CO2, all those things. So we have to figure some things out. There is some hurdles here. Now, once we have handled the hurdles, so what are the effects on the environment? Now, first, because we are gonna use solid state in the future, we don't have to worry about emissions, continuous emission, as in, of course, there will be emissions once we were doing the drilling. Once the drilling is done, there won't be any emission. Then we don't have to worry about earthquakes. So awesome. Then you have to, I have seen so many YouTube comments that they're like, you know, if we do this, we're gonna cool the earth. Do they not know we barely need 100 terawatts of power? Barely. We right now only consume 23 terawatts of power. So for that reason, saying that we're gonna need, cool the earth, they forget to understand that the amount of energy that it has, it's so much that 100 terawatts taking out of it will not even make a 1 degree Celsius drop. And you have to understand, I'm not even talking going as deep as like upper mantle, I'm talking about in the crust. And if, let's say, you might say, hey, what if that area starts to cool down? Of course it will cool down, you're taking energy out of it, it will cool down. How much, that we have to figure it out only by testing it. We can't test it out on a computer. So let's say it cooled down to 1 or 2 degrees Celsius, that area became hard. Of course it happens, tectonic plates become hard if they get cooled. Now what will happen? Tectonic plates move. Over time nature will simply correct it, it won't even make a dent. So this whole idea is going to cool the earth and kill the magnetic field, no. Like, you have zetawatts of power here and we barely wants to take terawatts. Earth is not even going to notice it. And not to mention, earth is cooling anyway, might as well use that power, it's cooling anyway. And because we are using a solid state, we're not going to have to worry about any emissions. And the reason why I want to use Stirling Engine, as I already mentioned, we don't want to waste water. Water is a precious resource. So for that reason, these are the effect on the environment. If we use a Stirling cycle, we don't have to worry about wasting water. If we use solid state, we don't have to worry about emissions. So this was my presentation on future of infinite geothermal. I hope you liked it or learned from it. In that case, please leave a like, and if you didn't, dislike it. And I would suggest leave a comment what you want to see in the next episode of Future Friday. I hope to see you again, and please subscribe. Press the bell icon if you're free. And as always, thanks for watching.